Thank you for introduction. Hi, good afternoon. I'm Liwei from National Taiwan University. Today I'm very happy to present our latest project on wearable interfaces, Cyclops. Wearable and single-piece full-body gesture input devices. It is supposed that the most effective interface is the interface that we are trained to manage it at the longest, which is not our smartphone, but our body. Well, if you think about body this way, when we were infants, we received tremendous training to learn how to step out. Until now, we still train 24 hours to get familiar with various body skills. So this research Cyclops introduced a single device that enables full-body interactions. For full body, we mean being able to detect movement on various body parts, such as how users move their head, their shoulder, and even their legs. Well, doesn't it sound familiar to a famous technology, Kinect? Well, the problem of Kinect is that the interaction realm is limited to what's visible to the Kinect, which means users cannot move around. So to free the users from the constrained locations, on-body cameras were placed on various body parts to enable wearable interaction zones. For example, Digit from WIST 2012, where the camera on the wrist allows for hand interactions. But the movement on the other body parts are not visible to that cameras. So with camera on the shoulder, OmniTouch allows an interaction zone in front of the user's chest, allowing for touch interface everywhere. And with camera on shoes, the shoe sense allows a much greater interaction zone that covers for upper body. However, the movement of the user's feet are not visible to that camera. Finally, to cover full body interactions, another approach is to distribute motion sensors all around the body, such as using accelerometers. But it is more cumbersome to put on sensor suit, if not for professional applications, which is similar to wearing this motion capture suit, as you can recognize from the face of this helpless man. So just a quick video to show what Cyclops is about. So it's a fisheye lens camera placed on user's center at the center of the chest, and to enable many full body interactions. I hope you get the idea. So Cyclops is a single-piece wearable device that sees all. The idea is very simple, that we use fisheye camera. Imagine that you have a fisheye camera at the center of the chest, and the yellow shadow here indicates the body parts which are visible to the camera. So the Cyclops sees the chin, sees how users move their hands, and also their legs. The question is, how wide is wide enough for a camera on the chest to see the full body? Let me give an example. This is a GoPro, and this man is riding on a motorcycle. So from the view taken by the GoPro, on the top you can see, we can still see the hands on the handle. But where are the feet? Well, what if this man is standing on a motorcycle like this? Well, for safety reasons, it may be important to prevent young kids from doing this. So let's back to the question, how wide is wide enough? Here, the green area indicates the camera field of view, and the green shadow displays the body part which are visible in the camera. So how wide is wide enough for a camera to see a body like this? Another example, on the left is the image also taken by the GoPro, and the green shadow indicates the body part which are visible. Still, we are missing the chin and the user's legs, right? So finally, we got this super fisheye lens, which gives us 235-degree field of view. From here, we can clearly see the chins on the top, which indicates where the head position locates, and almost the entire hands on the sides, and also the user's leg on bottom. But comparison, there is a huge difference between these two lenses. And this gives us the sense for full-body interaction. So, proof of concept device. The Cyclops lens at the center is surrounded by a set of infrared LEDs. Well, instead of using color image, we use infrared image to facilitate foreground extraction for full-body interaction. And we also added an IMU to the Cyclops for two purposes. First, it helps reorient the image to upright in case that users might put on the device improperly. And second, the orientation data from IMU is helpful to distinguish body gestures of different orientations. Wearable phones, there are several possible wearable phones for Cyclops. It is interesting that when you have an extreme field of view, it really doesn't matter either you put the lens to the upper or lower side of the body. That we also proved this in the experiment. So just a video, here you can see me wearing the Cyclops lens working in this messy lab. So you see me, I have a drink on the hand and to take a sip. You see my legs on the bottom, right? So again, while I'm working, you see the legs appear and disappear repeatedly. So give us a sense that what the Cyclops looks like. And yeah, again, we did not take the color image. We instead used the infrared image to prove the concept. And this is a few examples of what we have. So pipeline of body gesture recognition. On the left, the user is doing a motion gesture. And for every image frame, we first did the foreground extraction, then aggregate the foregrounds into a motion history image, which is then fed to a gesture recognizer to determine the gesture type. So foreground extraction. For each input image, we first reorient the image according to the orientation data from the IMU reported. Then we take a ring at the edge and straighten it into a strip. Then did the foreground component extraction. So the reason we can do this is because the property of ego-centric image that whatever user do, their movement, their body limb must enter the image from the edge. And this, by using this trick, we are able to very effectively identify candidate foreground body limbs. So then we take these candidate body limb positions and also the edge map as an indicator for region filling, and now we get the foreground. Then all the foregrounds we aggregate into a motion history image, which is an image template that encodes both the temporal and the spatial information of the motion. So another example. Here, this student is doing some simple exercise. On the top is the raw data image. And on the bottom left are the foregrounds, which you get through the process I just mentioned. And also on the right is the motion history image. You can notice that how the motion history image encodes both the spatial and temporal information in its intensities. And once we get the motion history image, we are ready for gesture recognizer. Well, there are a bunch of gesture recognition algorithms that we could borrow from machine learning and computer vision. But by the time we were most interested in the temporal matching, and we purposely choose this straightforward method to show the potential of ego-centric image for full-body gesture recognition. The experiment. In the experiment, we collected 16 motion gestures and 4 stationary gestures from a workout set. 20 participants were recruited for recording the gesture data. On the bottom is the corresponding motion history image of a participant, which we call IMHI. We also take a different version of motion history image called the DMHI, which is obtained by aggregating the difference between foregrounds over time. In comparison, DMHI further emphasizes the motion aspect of the gesture. So here's the experimental result. In the leave one person out evaluation, the result actually is not bad. Well, which is not good, but not bad. So the temporary matching achieved about 80% recognition rate. Then we turn to a more advanced machine learning approach called RDF, the Random Decision Forest, which is very popular in many computer vision applications. So we follow a typical setup, but here I will not touch the detail. You can check the paper for how we adopt RDF for training and testing. And surprisingly, the result is quite good. The performance raised by 10% to 90% recognition rate. Then we further did a multi-layer RDF, which incorporates orientation data from MU to build a two-layer RDF for gesture recognition. And the result rises to 92% recognition rate. So to test the feasibility, we did a second experiment with offset. You know, when the device is worn not so properly, we want to know how the offset impacts the performance. Then we collect another set of training data where the Cyclops is worn by an offset of 30 millimeters in 4 directions. And in the experiment, the original data are used for training, and this new offset data are used for testing. Well, even with the offset, result shows that we can still achieve 86% recognition rate using RDF method, which is actually nice, and the kind of proof of the feasibility of Cyclops for practical use. Now I'm going to show you the application that we have.
Okay, prepare yourself for sit-ups.
So the first application is interactive body workout. Here the workout helper will inform the users what's the next workout gesture.
Prepare yourself for crunches.
And inform them
Lift
to
your
prepare
left
for
leg.
that.
Next action, leg lift and toe touch.
And if the user did the workout too fast, it will inform him to slow down or vice versa.
Awesome. Next action, leg lift and toe touch. 2.
And the second application, mobile racing game. The Cyclops can expand the input modality of mobile phone. So here, this racing game users can use their full body interaction to interact also with the mobile game. So you see, to speed up, you just push their hand forward to as if they were holding the imaginary stick. And move the phone forward, which is recognized by Cyclops, that the game will enter the engage mode. And to brake, you just step his legs to the side. So it's more intuitive than just pressing buttons on the screen on the mobile phone. And the third application is a motion tracker for virtual reality display, such as Cyclops. So in this immersive gaming, our user is not restricted to where the Kinect is, but they can also very easily to turn any directions and still having the good gaming experience. And we support several gestures like the tag or power attacks. And lastly, not only for human, that we can still put the Cyclops on the door, on the toys, or even the animal to recognize the body gestures. So here I want to discuss more some limitation of current Cyclops. First, computer vision challenge. Our implementation adopts the infrared image to facilitate foreground extractions. But even so, the Cyclops still suffer from clutter in the environment. In this case, a future version of Cyclops using a fisheye depth sensor would help a lot, and we are expecting for that. Second, social acceptance. Regarding the chest-mounted devices, the social acceptance level between male and female users actually is quite different. In fact, our first challenge by the time was to find a female participant for recording gesture data. And in addition, there is a huge difference between the images taken by the male and the female users, because the body structure are quite different. So the image also very different. And the future work needs the further study and the proper design to include female users. So to wrap up, Cyclops is a single-piece wearable device for full-body gesture recognition. The main contribution is essentially the data, is essentially the idea which is proved by our prototyping using a super fisheye camera. And we hope that we could bring this idea to next level for a wearable version of Kinect in the future. Thank you, and I'm ready to take the question.
All right, for everyone who just joined, the microphone's in the middle there. And there's the first question.
So hi, Jens Grubert from Graz University of Technology. I really liked your work, and I was wondering, did you consider extending your approach to continuous input? I mean, now you're recognizing gestures, postures. How about if I would just like to have a slider on my arm? And I think, yeah, that would be a nice area. Have you any comments on that?
Yeah. Thank you. Very good questions. Currently, we only have the discrete gesture input. Yeah, and we also think about that. Using RDF actually, using the RDF random decision forest, it is possible to do the continuous gesture recognition, not gesture recognition, but continuous body tracker, just like a Kinect did. And we are currently working on that part. But the problem is that we got to get some good estimation to the depths. Like we only have the infrared image now, and it's very difficult to estimate the depth from the infrared image. So I think it's possible for like a future version with the depth sensor, then we could, we would like to work toward that direction.
I'm Jun Sang-Lee in Gonggung University. So I'm just wondering, is it able to improve if some setting small mirror to reflect your body and see your whole gesture?
Sorry? What?
Do you want to go a little closer to the microphone again when you re-ask the question?
I mean, some kinds of gesture like...
Can you go really close to the microphone?
Yes. Kind of this gesture can recognize because... So is it possible to set up a small mirror
Okay.
to reflect your body? Is it can improve your experience?
Yeah, okay. Actually, the other kind of